So you might have noticed that we pretty much skip over chapter 5. Chapter 5 kind of helps with chapter 6. So what I'm going to do is today I'm going to cover just a little portion of chapter 5, just enough of chapter 5 to help us with chapter 6. I feel like the rest of chapter 5 is really not necessary when we can use all that stuff in the actual context of chapter 6. So I don't have a specific homework in Wiley Plus for chapter 5. Instead, there's a few, like just a handful of questions from chapter 5 that are in your Wiley 6.1 homework. And other than that, then we're just going to, like I said, we're going to apply everything to chapter 6 and beyond. All right, so up to this point, we've used randomization distributions to do hypothesis tests, and we've used Bootstrap distributions to do our confidence intervals. And here's just a few of the different Bootstrap and randomization distributions that we've looked at. And you've probably noticed something similar about all these distributions as we've been looking at them. What seems to be in common with all these different distributions? Yeah, they're all bell-shaped, right? So they're all bell-shaped distributions. They all seem to have that same characteristic bell shape. And we've just been calling it kind of bell-shaped distribution up to this point. But distributions that have this characteristic bell curve to them have a special name, and we actually call them normal distributions. So let's talk for a minute about normal distributions. So a normal distribution is that, beautiful bell-shaped distribution. In fact, I think I have one on this page here. So all normal distributions are bell-shaped, they're symmetric, single-peaked, they look like this. There's lots of different normal distributions out there, and if we want to identify a particular normal distribution, then all we have to do is give its mean and standard deviation and say that it's a normal distribution. So normal distributions are identified by their mean and standard deviation. So normal distributions are identified by their mean and standard deviation. And the notation that we're going to use for a normal distribution looks like this. We're going to have a capital N, and then in parentheses, you put the mean and the standard deviation. All right, so that's how we list it. So normally the mean and standard deviation are going to be numbers. So we might say like normal 3510 or something like that. That would tell me that it's a normal distribution. It has a mean of 35 and a standard deviation of 10. So this is the notation that we use. And the reason why we talk about normal distributions is that they can be used as a mathematical model for many types of distributions. So normal distributions can be used as a model for many types of distributions. So on the previous slide, we saw that pretty much in general, randomization distributions, Bootstrap distributions, they tend to have that characteristic normal distribution look for them. And if you remember, the whole reason why we were doing Bootstrap and randomization distributions is because we were trying to mimic the sampling distribution. So the key idea here is that we're going to start to use the normal distribution as a model for our sampling distribution. So instead of using Bootstrap and randomization distributions to help us come up with p-values and construct confidence intervals, instead we're going to use the normal distribution to model the sampling distribution, and we're going to be able to use the normal distribution to help us come up with p-values and construct confidence intervals. So in parentheses here, I'm just going to say including sampling distributions. And then the last point here is that we're going to use areas under that normal curve to help us find the p-values and construct confidence intervals. So really, I mean, this is kind of the point in the semester where the statistics class is going to get a little bit more mathy, so to speak. You guys all had calculus as a prerequisite for this class, right? So when I start talking about finding areas under curves, you're like, oh, totally. I loved that in calculus. All I had to do is integrate and I could easily find the area under curves. So I'm totally on top of that, right? No, I see a couple of people shaking your heads. Wait, you didn't take calculus? Are you sure? I mean, it was one of the prerequisites for this class. Nah, just kidding. Okay, sorry to make everybody get a little anxious for a second here. Obviously, you didn't have to have calculus before taking this class. So we're not going to be using calculus to help us find areas under curves. Instead, actually in our class, we're mostly going to use stat key, which is going to help us find the area underneath the curve. But that kind of helps you get an idea of, okay, that's what it is doing, is just finding the area under the curve for us and making it so that we didn't have to have calculus to have this class. All right, so again, here's what our characteristic normal bell-shaped distribution looks like. And we talked about how a particular normal distribution can be identified by its mean and standard deviation. So this picture just kind of shows you how different normal distributions would look based on their means and their standard deviations. So this black curve right here is a normal distribution that has a mean of 0 and a standard deviation of 1. The one right next to it has a mean of 2 and a standard deviation of 1. So what you're supposed to get from this is that, look, they look identical except for one of them is shifted over. So if two normal distributions have the same standard deviation but different means, they're going to look the same, only one is going to be shifted one way or the other. On this picture over here, now we have 3 normal distributions. They all have the same mean of 0, but they have different standard deviation. So we have one with standard deviation of 0.5, one with a standard deviation of 1, one with a standard deviation of 2. And the idea is, remember, we're using this normal distribution as a model for when we do probabilities, like p-values, then it's kind of a model for probability or to represent all of our values. So the area underneath our curve always needs to add up to 1. Like regardless of what the mean and standard deviation are, then the area under the curve is going to add up to 1. So that's why you see here that these are all bell-shaped symmetric distributions. But if your data is more spread out, okay, then you still have to have an area of 1, so it's going to be a little bit squattier looking distribution for the same mean. So you can see that they all have the same area underneath them. It's just some have that area a little bit more spread out than the other ones do. All right, so, and this is kind of the main reason why this is going to be useful in our class is because of this thing called the central limit theorem. Okay, and the central limit theorem basically tells us that as long as our sample size is big enough, then our sampling distribution is going to follow a normal distribution. For pretty much all the statistics that we look at in our class, that's going to be the case. And so this is a pretty great thing because it's saying, hey, no matter what your original population looks like, we're going to be able to use this normal distribution, this one distribution here, to model the sampling distribution and then do things like find p-values and construct confidence intervals. Okay, so first of all, like the central limit theorem, what it basically says is that if n is large, then the distribution of many common sample statistics, or in other words, the sampling distributions, can be approximated with a normal distribution. So if n is large, the distribution of many common sample statistics, and when we're talking about the distribution of the sample statistic, we're really talking about the sampling distribution. Just 2 ways to say the same thing, can be approximated with a normal distribution. All right, and as I mentioned, this is important because this means that we're going to be able to use normal distributions to answer questions about these sample statistics, do things like p-values, confidence intervals, regardless of what the shape of the original population is. So that's pretty significant. We're just saying, hey, it doesn't matter how skewed or how wacky your original population is, as long as my sample size is large enough, the sampling distribution will follow a normal distribution. So I can just use the normal distribution to model it, and I'm good. So it's important because it means we can use normal distributions to model our sampling distribution, regardless of the shape of the original population. All right, actually the central limit theorem is like really the reason why you don't have to have calculus before coming into our class, because if we were trying to find the areas under a whole bunch of different types of curves, then that's when we'd have to be like, okay, fine, you better actually learn how to do calculus to do this. But because like everything kind of points back to a normal distribution, then we're gonna be like, okay, well, we can have other ways to find areas under normal distribution curves. So we won't make everybody learn calculus to take this class. All right, and one key question that you might be wondering, because everything says if n is large, so you might be wondering, how large is large? Well, how large it needs to be depends on the type of analysis that you're doing. So for every section in chapter 6 that we're going to cover, we're going to have a particular rule or condition for the central limit theorem to kind of work, I guess, and for us to be able to use the normal distribution to approximate the sampling distribution. So how large is large? It's going to depend on the specific type of inference that we're doing, and there'll be a separate sample size requirement for each type. So it depends on the specific type of statistical inference we're doing. There will be a sample size requirement for each particular type of statistical inference. So let's look at a little example of how we're going to be able to use a normal distribution and find an area under the normal distribution curve to answer a question. So this particular one says IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. A genius is somebody with an IQ about 140 or higher. So we want to know what proportion of people have IQ scores above 140. And because we know these are normally distributed, we know the mean and standard deviation of all IQ scores, then we can use area under the normal distribution curve to answer this question. So my first question, though, before we get to that part, is what's the correct notation that we would use to describe the distribution of IQ scores? So remember when we talked about notation for a normal distribution and how we did that, how would you write that specifically for this IQ data here? You can type it in the chat window if you're feeling bold and brave. Oh, there we go. Look at that. Look at all those great answers. So yeah, we would use the n, and then in parentheses, first number we're going to put is the mean, which in this case was 100. Second number we're going to put is the standard deviation, which in this case was 15. So n 100 comma 15 exactly. All right, so now we're going to use stat key to find the proportion. So if you have, I recommend that you open up stat key on your computer and do this along with me. So I got to get it open on mine, and then I'm going to share my screen with you. All right, so if you have stat key open, then you notice that in kind of the third clumping of stuff, third thing down in stat key, then it says theoretical distributions. And the one that we're going to be looking at for now is this normal distribution. So you're going to go to where it says theoretical distributions, then you're going to click on normal. And when you do that, it brings up this lovely bell-shaped symmetric normal distribution curve here. And if you look in the upper right-hand corner over here, then if you click on edit parameters, it will let you enter whatever mean and standard deviation that you want to. So I'm going to click on edit parameters. I'm going to put in 100 for the mean and 15 for the standard deviation. And then I'm going to click on OK. And then you can watch your normal distribution. Notice that the shape and everything stays the same. The only thing that's really different now is it's changed our scale down here. So we can see that now this normal distribution is centered right on 100, the mean, and it changed the spread as well so that it reflects a standard deviation of 15. All right, so think of this curve as just smoothing out what we would see if we had dots for every person in the population. Okay, and instead of counting dots to figure out, what proportion of people have IQs above 140, instead we're just going to find the area underneath this curve that corresponds to 140 or greater. So to do that, in this case, I'm looking for people with IQ above 140. So since I'm looking for above or greater than, then I'm going to click on right tail. So up in the upper left-hand corner where it gives you the options, you're going to choose right tail because in this case, we were looking for above 140 or greater than 140. Once you click on right tail, then the bottom box underneath the graph is where you're going to enter in the value that you're interested in. So in this case, we were interested in 140. So I click in the bottom box underneath, I type in 140. Now you can see that it shaded the part that I'm actually interested in. I want to know what the area of that little red shaded region is there, because that's the area above 140. And once I've put in the 140, then the little floating box here actually gives me the answer. So 0.0038 is the answer that I'm looking for. That is the proportion of people who have genius IQ scores. So here's kind of a I guess, step-by-step approach to what we just barely did. Okay, so we entered in our parameters, then we clicked on right tail because we wanted to know greater than, we put in the quantity that we were interested in, and then the answer is in the floating box. All right, we've talked about normal distributions. We said that there's lots of different normal distributions, and the only thing really different about different normal distributions is they have a different mean or different standard deviation. But there is one particular normal distribution that is a special normal distribution, and it's used more than any other. So we give it a special name. It's called the standard normal distribution. So the standard normal distribution is a special normal distribution that has a mean equal to 0 and a standard deviation equal to 1. So it's a special normal distribution with mean equal to 0 and standard deviation equal to 1. So in our normal distribution notation, that would be normal 0, 1. There. And the reason why it's so special and why we talk about it specifically is because all other normal distributions can be made to look like the standard normal distribution. So all other normal distributions can be made to look like standard normal distribution. All right, so this is kind of a bonus because it basically means that we really, not only does everything look like a normal distribution, so all we have to use is a normal distribution for now anyway, but we can make all the normal distributions look like the standard normal distribution. So basically we can boil it down to only using the standard normal distribution for all of our problems. So that's going to be kind of handy. And the way that we make other normal distributions look like the standard normal distribution is that we're going to standardize. So to convert a value from any normal distribution, all we need to do is standardize. So to convert a value from any normal distribution, we just need to standardize. Okay, when you hear the word standardize, does that make you think of anything? We talked a little bit about standardizing back in, I believe it was section 2.3 when we started talking about standard deviations, making sense of the standard deviation. And we said one way that we kind of use standard deviation is to compute something that will help us kind of put everything on the same scale. Oh, yes, perfect. Okay, so over there in the chat window, Lane said it's a z-score, and that's exactly right. So when we're talking about standardizing, we're really just essentially computing a z-score. Okay, and if you remember, z-scores change things. So instead of measuring in IQ score units, for example, we start measuring in number of standard deviations away from the mean. So in general, to standardize, then we're going to compute our z-score or our z-value by taking a value minus a parameter and dividing it by standard deviation. So when we start using this in the context of a sampling distribution, then the standard deviation that we're going to be using is going to be the standard error, because we're going to be looking at the standard error of whatever statistic that we're looking at. If we're just talking about individual values like we are with these IQ scores, So for the IQ scores, we're looking at a single value, and we would just subtract the mean and divide by the standard deviation. So this is what it looks like just for individual values. But this is kind of the general format that we're going to have when we're computing z-scores, kind of moving forward. All right. Oh, here's a picture of what the standard normal distribution looks like. Lovely. Mean of 0, standard deviation of 1. So thinking back to our IQ problem here, if we were going to use the standard normal distribution, then all we do is we convert our 140 to the equivalent score in the standard normal distribution, which we do just by computing the z-score, and then we can use the z-score to help us find the area under the curve. So we're going to do that. So we'll start by finding the z-score. So remember, to find the z-score, we take the value we're interested in, we're going to subtract the mean, divide by the standard deviation. So in this case, that would be 140 minus 100 divided by 15. That gives us a z-score of 2.667. Okay, remember, that means that geniuses then are 2.667 standard deviations above the mean. And what was kind of our cutoff for like an unusual observation back when we started talking about z-scores? Anybody remember? Like in order to be unusual, yeah, then we said that it had to be above 2 or below -2, right? So a z-score of 2.667 is definitely unusual. So it's unusual to be a genius, which makes sense. Okay, so let's go back to StatKey and let's look at how we would find this area if we're using the standard normal distribution instead of the normal distribution that had a mean of 100 and a standard deviation of 15. All right, so back in here, then sometimes the easiest thing to do is just to go all the way back out and then click on normal distribution again. That resets your parameters, it resets your plot and everything else. If you're keeping the parameters the same, you could just hit reset plot and that would do it. But if you just always want to be on the safe side, I usually just go back out and come back in. Then I just make sure I'm starting with a clean slate every time. All right, so this time I'm going to leave the mean as 0 and the standard deviation of 1. Notice that it is the standard normal distribution that is the default that comes up right when you come in to the normal distribution on StatKey. And instead of looking for the area above 140, I'm going to be looking for the area above 2.667. So same idea, because I'm looking for the greater than or above area, I'm going to click on right tail. Now in this bottom box down here, I'm going to put the z-score, which was 2.66666 repeating. So in StatKey, they kind of like it rounded to 3 decimal places. So I'm going to put 2.667. And when I do that, notice my little floating box says 0.0038, which is exactly the same answer that we got doing it the other way. Okay, so you can see that either way, we're going to get the exact same answer. But in general, what we're going to end up doing in our class is using this standard normal distribution because we're going to be computing a z-score type calculation and using that to find our p-values and stuff like that. So this is more similar to the process that we're going to be using in just a few minutes when we talk about how we're going to start applying this information. Okay, so back here again. Okay, here's the general plan for doing that when you use the standard normal curve. I want you to take like 2 or 3 minutes here and see if you can find all of these areas under the standard normal curve using StatKey. Okay, and then write them down in your paper and we'll see if we all got the same thing. So you want to find z below z equals -0.85, above z equals 1.25, and above z equals -1.75. All right, it looks like a bunch of people are done, so let's talk about these. So for the first one, below -0.85, then we're going to click on left tail because we want to know below. Then we're going to put that -0.85 into the bottom on StatKey, and that will give us an area of 0.198. For the second one here, above 1.25, this time because we want to know above, we're going to click on right tail. We're going to put the 1.25 down in the bottom box. That's going to give us 0.106 in the floating box there. and the last one above negative 1.75. So I want to know above, so I'm going to click right tail, but my box is going to be over here, so it's a little tricky. So I put the negative 1.75 in my box, and then it highlights all this area because there's a bunch of area that's greater than negative 1.75. So it gives me an area of 0.96. All right, so how'd everybody do? 3 for 3, 2 out of 3, 1 out of 3. All right, great. Okay, so now let's start talking about how we're going to be able to apply this to something really great and useful, like actually doing a hypothesis test or a confidence interval. And each section of chapter 6 is going to talk about a different type of statistical inference. So that's kind of one of the nice things about chapter 6 is that in chapters 3 and 4, like every problem could be something different. You could do one problem that was one mean, another problem that was two proportions, another one that was correlation. And every time you're doing the same basic things, but you had to kind of remember, okay, how do I write the hypotheses for this? And how do I define the parameters and do all that stuff? Well, here in chapter 6, all of section 6.1 is going to be one proportion. And next time we're going to do 6.3, and all of that is going to be two proportions. And so on for each of the 5 different sections that we have in chapter 6. So that'll kind of help us to really focus, and it'll make it so that you get a lot of like repetitive practice doing the same type of thing. So I think some people tend to like that approach. Okay, so we're talking about the distribution for one sample proportion, because we're going to do inference for one proportion. So that means we need to talk about the sampling distribution for p hat. And the mean of the sampling distribution, as we've already learned in other chapters, is equal to the population parameter. So in this case, that means that the mean would be equal to p. And the standard error of the sampling distribution can be calculated using this formula here. So square root of p times 1 minus p over n. And the shape is going to be approximately normal if the sample size is large enough such that n times p and n times 1 minus p are both greater than or equal to 10. So let's look at a little bit of application for this. So this just shows just in regular notation, normal distribution notation. P hat follows an approximate normal distribution with a mean equal to p and a standard deviation equal to square root of p times 1 minus p over n. And we said that this is a good approximation as long as n times p and n times 1 minus p are both greater than or equal to 10. So that whole sample size requirement, this next slide is just going to kind of show how why we have that requirement essentially. So if our p is 0.5, we have a sample size of 1, this is what the sampling distribution would look like. So clearly not a normal distribution. When p is equal to 0.5 and n is equal to 10, you can see that by the time I get 10, this actually looks just like a normal distribution. It looks pretty lovely. And if I have a sample size of 30, like definitely beautiful, gorgeous, normal looking distribution. Sample size of 50 and 100, we're good. Okay, so when my p is 0.5, thinking about that n times p and n times 1 minus p both being greater than or equal to 10, we can see that even by n equals 10, which actually wouldn't meet that requirement, but certainly by n equals 30, we have a definite normal distribution here. So we can see that the normal distribution would be a good approximation for that sampling distribution. When we have a p of 0.7, then you can see that it takes a little bit bigger sample size, maybe more around 50, for the sampling distribution to follow a good normal distribution. So we need a little bit bigger sample size when I have a p of 0.7. And when I have a p of 0.1, I need even a bigger sample size before my sampling distribution looks like a normal distribution. So basically that requirement, the NP and the n times 1 minus p, is just making sure that our sample size is big enough that the sampling distribution actually does follow a normal distribution. So we can use the normal distribution as a model. So here's one example. The 2010 census reports that all of the nation's occupied housing units, 65.1%, are owned by the occupants. So if we were to take random samples of 100 homes, what would be the standard error of p hat? So first, looking up here, this 65.1, is this a parameter or a statistic? Yeah, this is a parameter, right? This is P. We know it's a parameter because it came from the census, which measures everybody. Okay, so this is a parameter. So it's saying, okay, in the population of everybody, 65.1% of people own their or live in something that they own. So let's say now that we take a bunch of random samples of size 100, from each of those samples, we're going to calculate p hat. And if we look at the distribution of p hat values, what would the standard error of that sampling distribution be? So looking back, and there's way too many clicks here. Okay, we can see that the standard error of that sampling distribution is going to be equal to the square root of p times 1 minus p over n. So we're just going to do that calculation. That's going to tell us the standard error. All right, so standard error is equal to the square root of p times 1 minus p divided by n, and we square root that. So in this case, the p was 0.651, so I'm going to have 0.651 times 1 minus 0.651 over 100, and then square rooted. So hopefully you brought your calculators today. Let's go ahead and plug this in and make sure that everybody gets the same answer. So I like to do everything underneath the radical first, and then take the square root of that answer. So I usually do 0.651, and then if you want to use parentheses on your calculator, then you can hit times parentheses 1 minus 0.651, and then divided by 100. So mine kind of looks like that a little bit. All right, then I'm going to take that answer and find the square root of that. So to do that on my calculator, I hit the square root button. So my square root button is right here. So I'm just going to click the square root there, and then I'm going to put answer down here so that it says square root of the answer, and then I can hit equals, and I get 0.04766. So it ends up being 0.048. All right, how'd you guys do? Did you guys all end up with that 0.048 answer? Yay, I see some thumbs up. That's good. I see, oh, 2 thumbs up even. So overachiever. Okay, excellent. And if you're having any problems with your calculator, please stay after class and I can work through it with you. Usually it's just like a simple matter of like putting things in the right way, and we can get that fixed for you so that doesn't cause any problems for you. So this next slide is just kind of showing you, hey, remember, we used to figure out what the standard error was by looking at a dot plot of our sampling distribution and then using the standard deviation of that dot plot as our standard error. And this is just showing that, hey, we basically just used a formula to get the same answer that we were getting using this dot plot. So we're showing that we're getting very similar results either way. Okay, it's kind of showing us that, hey, normal distribution is actually a pretty decent approximation for this sampling distribution. Okay, another question. So still on the same idea, the census reports 65.1% are owned by the occupants. We have the standard error. So if we were to take random samples of 100 homes, how would we write down what the distribution of p hat looks like? So here's a list, A, B, C, D. Which one of these is the correct notation for describing the distribution of p hat values? You might have to go back in your notes and look at how we describe the notation, which number goes first, which number goes second, or what each of the numbers are. There we go. So yeah, A is the correct answer. So remember, we say normal distribution, and then we list the mean and the standard deviation, which in this case is the mean and the standard error of that sampling distribution. So the 0.651 and the 0.048. Okay, here's another one we'll do real quick. So the 2010 census reports 14.6% of the residents of Oregon speak a language other than English at home. If we were to take random samples of size 100, what would the standard error of p hat be? So I'll give you a second to see if you can figure that one out on your own before I show you the answer. It's basically the same thing we were doing before, so just use that same formula. All right, so from this drop-down list, which answer looks closest to what you got? Perfect. Whoops, I thought it was going to show the equation, but it didn't show it. So we just take 0.14, or square root of 0.146 times 1 minus 0.146 over 100. That's what gives us that 0.035. All right, so then looking at this list, which one of these would be the correct way to describe the distribution for that sampling distribution of p hat for this example? Yes, D. Okay, so it has the mean equal to the value of the parameter, which was 0.146, and a standard deviation equal to 0.035. All right, so now let's look at how we can use all this information to help us do a hypothesis test. So first of all, think about the steps for a hypothesis test that we talked about in chapter 4. First part is we're going to state the hypotheses. We're going to do this the same way that we did in chapter 4, so nothing's changed there. Second, we're going to collect the data and calculate the sample statistic. Again, nothing's changed there, same thing. Step 3 is where we have a few little differences come in here. We're still going to be examining the evidence, but instead of creating a randomization distribution to help us find the p-value, what we're going to do is we're going to compute something called a test statistic and use that to help us find the p-value. So a test statistic is usually a standardized form of your sample statistic. So I'll kind of write that little definition here. So test statistic, kind of our definition is that it's usually a standardized form of the sample statistic. So usually a standardized form of the sample statistic. And again, when you think of standardized, you're thinking z-score, right? And that's basically what we're going to do. So that how we create a z-score is we take our value, we subtract the mean, we divide by the standard deviation. And that's what we're going to do here to get our, that says statistic, to get our test statistic. So our general format for a test statistic is going to be a sample statistic. We're actually going to subtract the null value because that's what we're assuming that the parameter is under the null hypothesis, and then we're going to divide by the standard error. So typically we're going to take our sample statistic minus the null hypothesis value, whatever we're claiming that the parameter is under the null hypothesis, and we're going to divide by the standard error. And then we're going to use that along with the normal distribution, like in StatKey, to help us find the p-value. And then we're going to draw conclusions. So our conclusions are still going to be based on our p-value, the whole if p is low, HO must go, like all of that. We're still going to do all that. We're going to write our conclusions exactly the same. So the only real difference between this chapter and chapter 4 is just the method that we use to arrive at the p-value, and everything else is the same. So here's kind of what I was saying before. So this is the general format for a test statistic. We're going to have our sample statistic minus the null value divided by the standard error. So when we're thinking about p hat here, we know that the sampling distribution for p hat has a mean of p, standard error of this thing, and we know that it's normal if all this stuff holds true. So I'm looking for something to plug in for my standard error here. And this is my formula for standard error. But if I look at this formula, okay, thinking about in real life where I'm going to take one sample, and the reason why I'm taking a sample is because I don't know what the population parameter is, then you might start to see a little problem with using this formula the way that it is, because it has p in it, and p is the population proportion, and we don't know the population proportion. That's why we're doing statistics in the first place. So when I'm doing a hypothesis test, then I'm going to have to use something in place of p. And basically, when I'm doing a hypothesis test, then I'm assuming that the null hypothesis is true until proven otherwise. And under the null hypothesis, I'm claiming that p is equal to some particular value. So when I'm constructing, or when I'm calculating standard error rather, then I can use p naught in place of p. So my standard error, when I'm finding my test statistic is going to be this. We're going to use P naught in place of P. Okay, P naught is going to be our well, since we're assuming that the null hypothesis is true, then it's going to kind of be our best guess for P for a hypothesis test. Plus, the other thing is that when we're finding a p-value, we're always doing it assuming the null hypothesis is true. And if the null hypothesis is true, then p is equal to p naught, so we could go ahead and use p naught. Okay, so then let's write this out a little bit more specifically. So when we're doing a hypothesis test for one proportion, then our hypotheses, okay, the null hypothesis is going to be that P is equal to something, okay? It's going to have a specific number when you're doing a particular problem. For right now, I'll call it P naught, but P naught is always replaced by an actual number when you're writing this out for a particular problem. The alternative hypothesis is going to be that P is either greater than, less than, or not equals to P naught, okay, or whatever that number is that we had up there. Okay, and the symbol that you use is going to just depend on what you're trying to find out. Like, look at the wording of the research question. For our test statistic is going to look like this. We're going to have Z is equal to P hat minus P naught divided by standard error, which is going to be the P naught, times 1 minus P naught over N. And that square root should really go all the way down. There we go. All right, so I have my sample value minus the null value and then divided by the standard error. All right, and if you recall, the conditions for using the normal distribution were that N times P and N times 1 minus P were both greater than or equal to 10. Again, we don't know what P is, so we're going to use P naught instead. So the conditions are going to be that N times P naught and is greater than or equal to 10, and N times 1 minus P naught also, that says greater than or equal to 10. All right, so let's go ahead and look at an example of how we're going to do a hypothesis test then. Let's go through the whole thing. Okay, so here's our example. Of the 2,430 Major League Baseball games played in 2009, the home team won in 54.9% of the games. If we consider 2009 as a representative sample of all Major League Baseball games, is this evidence of a home field advantage in Major League Baseball? All right, so the first thing that we want to do is we want to define our parameter and state our hypotheses. So first thing we're going to do is define our parameter. And remember, 6.1 is all about one proportion. So the parameter for 6.1 is always going to be P. Okay, we have to figure out what P is equal to. And P is a proportion, so we know that the first word to follow the equal sign is going to be proportion. Okay, and in this case, it would be the proportion of all Major League Baseball games won by the whole team. So proportion of all Major League Baseball games won by the home team. So we have our parameter here. Now we need to write our hypotheses. Okay, and the hypotheses are always written about the population parameter. So whatever I defined, that's going to go into my hypotheses. So remember, null hypothesis is going to be that P is equal to something. And then the alternative hypothesis is going to be that P is equal either greater than, less than, or not equal to the something. And so for this problem, we're trying to figure out if there's a home field advantage. So if there was a home field advantage, then that would mean that you were more likely to win at home, right? So there's two options, win at home, not win at home. If you're more likely to win at home, then that means that you would have to win more than half the time at home, right? So that means that the value that we're going to use for our P naught here is going to be 0.5, okay? Because if there's no home field advantage, then you would win about half the games at home, and half the games would be won by the home team and the other half would be won by the away team. If there is a home field advantage, then that would mean that more than half the games were won by the home team. So for my alternative, it's going to be greater than, because I want to know if more than half the games are won by the home team. So null hypothesis, P equal 0.5, alternative P greater than 0.5. All right, once I have my hypotheses, I've defined my parameters, then I would collect the data, which of course they've already collected the data here for us. They found that out of 2,430, so that's my N, then the home team won 54.9% of the time. So they gave me P hat. They won't always give you P hat. Sometimes they'll give you a count. Like they might just tell you that they won, I don't know how many that is off the top of my head, but let's say it's like 1,700. Okay, so they might just tell you that they won 1,700 games, and then you would have to compute P hat. Remember that P hat is a proportion, so it's always going to be a number between 0 and 1, or between 0% and 100%. So I've got my sample statistic here. So now I'm ready to actually do the hypothesis test. So the first thing I want to do is I want to check the conditions and make sure that it's okay for me to use the normal approximation. So remember that the conditions were that N times P naught and N times 1 minus P naught both had to be greater than or equal to 10. So let's go ahead and do that calculation. So N, I'll have to back up here, N is 2,430. So N, 2,430. Okay, P naught is the value we're claiming that P is under the null hypothesis. So whatever it says in the null hypothesis, that number, that's my P naught. Okay, so that's what I'm going to put here when I'm multiplying. So I'm going to have 0.5. So 2430 times 0.5, that's going to be equal to, I didn't leave myself enough space. Well, let me figure it out. So 2430 times 0.5 gives me 1215. Okay, so 1215, is 1215 greater than or equal to 10? Definitely. So far we meet the requirements. Okay, the requirement is that both of these quantities have to be greater than or equal to 10 though. So now I need to do it for the other one. So I'm going to have 2430 times 1 minus 0.5. 1 minus 0.5 is just 0.5 though. So we're going to end up with the same number here, 1215, which is still greater than or equal to 10. So yes, I do meet the conditions for doing this test. All right, so there's my hypotheses. The conditions, N times P naught and N times 1 minus P naught. We just did those calculations. They were both greater than or equal to 10, so we do meet those. So now we're ready to find our test statistic. So remember, our test statistic is that Z, it's going to be P hat minus P naught over the square root of P naught times 1 minus P naught over N. So here's the formula. Okay, then we're going to plug everything we know in there. So P hat, remember that came from our problem. They told us what P hat was in this case. It's 0.549. All right, and then P naught, that's the value claimed in the null hypothesis. So I'm going to have 0.549 minus 0.5 divided by square root of P naught, which is 0.5 times 1 minus 0.5 over N, which was 2430. So now you're going to do all those calculations. Now, the key here is don't round unless you have to, and then try not to round too much. So it's a good idea, if you can, to keep as many numbers in your calculator as possible. So, you know, if you can keep numbers in there, use the previous answer, whatever you have to do to keep as many numbers in your calculator as you can, or write down a whole bunch of decimals and then plug all those in. So keep as many decimals as you can until you get to your final answer, and then your final answer can be rounded to 3 decimal places. But you typically want to use more than 3 throughout your intermediate calculations, especially while we're working with proportions. It becomes a little bit less crucial next week when we start talking about means, but with proportions, numbers get really small, and if you start rounding too soon, you're going to get the wrong answer, and it's just going to make you cry, because then you're going to go into Wiley Plus, and it's going to tell you got it wrong, and you're going to be like, I know I got it right, I know what I'm doing, and so we just want to avoid like all those tiers. So just carry out as many decimals as you can. Keep the numbers in your calculator if you can. Okay, so hopefully in all my babbling, then you just had a chance to do these calculations, and I hope you got the same number I did, 4.831. So this 4.831, remember we called this our test statistic. And we're going to use the test statistic to help us find our p-value. And to do that, we're going to go over to stat key. So remember that number, 4.831. Okay, and also look at our hypotheses here. Notice that I have a greater than hypothesis here for my alternative. So those two things are going to help me figure out my p-value. So back here in stat key, I'm going to reset my plot. All right, and because my alternative hypothesis said greater than, then I'm going to click on right tail. Down at the bottom, I'm going to put in my test statistic, which was 4.831, I think. And click on OK. All right, and then what we're looking for is going to be all that area that is more extreme than 4.831. And you can tell by my picture here, there's practically nothing out there. And in fact, if you look at the floating box, anytime that stat key starts to use that little E, it's using scientific notation. So what this really means is 0.00000068 is what that is. Okay, so you're going to have 6 leading zeros and then the 6.8. So if I'm rounding that p-value to 3 decimals, you're just going to basically get 0. And it's okay to get a p-value of 0 or really, really close to 0. It just means that that would be super unlikely to happen due to chance if the null hypothesis is true. Meaning, remember, when we have a small p-value, it means that we have lots of evidence against the null hypothesis and in favor of the alternative hypothesis. So here's the picture from stat key. P-value of this thing, 6.8 times 10 to the negative. Why does it say 8? I don't know. It should say 6.2. Wait, why does that one say 6.2? Because I totally have the wrong number down there. Okay, don't look at my picture. Look at what we did together in class, because that one's a mess. Although essentially the same answer in the end, then we end up with p-value essentially equal to 0. All right, so if my p-value is 0, that's really, really, really low. And when p is low, then HO must go. So next I'm going to write my conclusion. I'm going to say we reject the null hypothesis. That means that there's strong evidence of a home field advantage in Major League Baseball. Or you could say it a little bit more structured. You know, there is strong evidence that the proportion of wins by the home team is greater than 0.5. The next example, I think I'm going to skip over because I want to make sure we get to confidence intervals here at the end. Oh, this is just showing, hey, if we do the same test with a randomization distribution, we essentially get the same answer out of it. So I do want to point out something about the next example, though, this order and choice. So in this one, they had these subjects and they were given 2 wines and they had to say which one they liked best. And they were under the impression that they were tasting 2 different wines and trying to decide which one was better. But in reality, they were being given the same wine, and the researchers were trying to figure out if the order of presentation made a difference, like if people were more likely to choose the first one or more likely to choose the second one. So for this one here, then this one's going to be a 2-sided test because we were looking for either way. We wanted to see if they were more likely to choose the first choice or more likely to choose the second choice. And if there was no difference between the two, then about half the time they would choose the first presented one and the other half they would choose the second presented one. So that's why we get the 0.5 in the null hypothesis. So the key difference about this one from the test we just did is that this one's going to be a 2-sided test. And So I'm not going to work out the calculations for the conditions here. Here's what our test statistic would look like. What I do want to talk about is how this is going to affect our p-value when we have a two-sided test versus a one-sided test. So working through the calculations for our test statistic, we would get a 2.121. So in stat key here, all right, then this is a two-sided test. So I can click on two-tail, but now I have to choose which box am I going to put the 2.121 in. And basically, if it's positive, I'm going to put it on the right. If it's negative, I'm going to put it on the left. So 2.121 was positive, so I'm going to put it over here. And once I do that, then for a two-sided test, remember that you have to double the tail area. So that means that either I add these two outside floating boxes together, or I double the value in one, same thing, to get my final p-value. So that's the key thing that I really wanted to point out from this one. So we're going to end up with a p-value of 2 times 0.017, which is 0.034. So in this time, we would also reject and conclude that we had sufficient evidence that the proportion of people who chose the first presented wine is greater than 0.5. So in other words, the order that you're given it does matter. People tended to like the first one better. Okay, so let's talk about now how we can do confidence intervals for one proportion. And when we talked about confidence intervals in the past, we said, okay, general formats for a confidence interval is going to be a statistic plus and minus a margin of error. And in chapter 3, when we wanted to use the standard error method, then we said, okay, margin of error can just be equal to 2 times the standard error. And who remembers where that 2 came from? Why did we use the number 2? Anybody remember how we came up with the number 2? It actually, oh, there we go. It actually came from the 95% rule, right? Because we said 95% of the values are going to be within 2 standard errors of the parameter in this case. So the 95% rule kind of brought in here. But because of that, then the only kind of confidence intervals that we did using this whole using a calculation with the standard error was a 95% confidence interval. So in this chapter, we're going to kind of expand that idea and say, okay, 2 is not the only number that we can use. We could actually figure out what a different multiplier would be to make a 90% confidence interval or a 99% confidence interval or any level of confidence that we want. So instead, we're going to find the margin of error by taking z star times the standard error. And z star is a critical value from the normal distribution. Basically, we're going to find z star by going to stat key. So I'll reset my plot. In stat key, you're going to click on two tail, and then you're going to put whatever you want your confidence level to be in the middle box here. And then the bottom box is going to be your z star value. So you can see for 95%, the bottom box says 1.96. That's why we were using 2, because 1.96 is pretty darn close to 2. So we just kind of rounded and said we're all good. But in this chapter, you're not going to use 2 anymore. If you want a 95% confidence interval, you're going to use 1.96. Okay, what if I want a 99% confidence interval? Well, then all I have to do is change the area in this middle box here. I'm going to change that to 0.99 and hit OK. Okay, if I have 0.99 in the middle, then it tells me the multiplier I need to use, that z star value, is 2.576. Same thing if I want a confidence level of 90%. Then I put that in, and now I'm going to use a multiplier of 1.645. Okay, and I can put whatever I want in there. If I want a 92% confidence interval, then just put the value in the center box. Whatever's at the bottom is going to be your z star value. Now, there are 3 values for z star that are used pretty much all the time in real life. I can't remember if Wiley Plus is going to throw a different one at you. If it does, you know how the process on how to find it. Otherwise, on your notes page, if you printed it out after I edited it, if you printed it out yesterday, you might not have gotten this on there, but if you printed it out more recently, then I did put a little box on there that just has the z star values for 90, 95, and 99, because those are pretty much the only Z-star values that you're really going to need. Okay, so let's talk about our formula then for figuring out the standard error when we're doing a confidence interval. So we know the standard error for p hat, this is what we talked about in the beginning of class, was square root of p times 1 minus p over n. However, in real life, when we collect a sample, we don't know p because p is a population value. So when we did a hypothesis test, we used p naught since we were assuming that the null hypothesis is true. But now that we're doing a confidence interval, we have no null hypothesis. So now what are we going to use? Well, we're just going to use our best guess, our best estimate for p, which in this case is going to be p hat. So we're just going to use p hat in the formula instead of p. So what that means is that our resulting confidence interval formula is going to be this one right here. We're going to have p hat plus and minus z star times square root of p hat times 1 minus p hat over n. And our conditions are going to be that n times p hat and n times 1 minus p hat are both going to need to be greater than or equal to 10. So make sure you write down this formula and then write down that the conditions are that n times p hat is greater than or equal to 10 and n times 1 minus p hat is also greater than or equal to 10. All right, and then remember p hat, that's just our sample proportion. Z star, we've talked about how we're going to find Z star, or, you know, like I said, really you can just, it's probably going to just be picking one of those 3 standard Z star values that now you have in table form there. And then we're going to have to compute the standard error here. And then once we have our confidence interval, we're going to interpret the confidence interval exactly the same as we interpreted confidence intervals back in chapter 3. So let's look at an example. In March 2011, a random sample of 1,000 US adults were asked, do you favor or oppose sin taxes on soda and junk food? And 320 adults in that sample responded in favor of the sin taxes. So we want to give a 95% confidence interval for the proportion of all US adults that favor these sin taxes. So first thing, let's define our parameter. So remember, this is section 6.1, so our parameter is always going to be P. And P is a proportion. So in this case, it's going to be the proportion of all adults who would favor sin taxes. So proportion of all adults. Whoops, that says adults. Proportion of all adults who favor sin taxes. All right, so there's no hypotheses to write, so we don't have to worry about that. We can collect the data, which we have here. It looks like they took a sample of 1,000. Out of that 1,000, 320 adults responded in favor of sin taxes. So my sample proportion, p hat, would be equal to 320 over 1,000, which is 0.32. Okay, so this is my sample statistic. Okay, next, I want to look at the conditions and make sure that I meet the conditions in order to use this method, the normal approximation, to construct my confidence interval. So to do that, for a confidence interval, I want n times p hat and n times 1 minus p hat to both be greater than or equal to 10. So n was 1,000 and p hat is 0.32. So that ends up being 320. Then this one is 1,000 times 1 minus 0.32, which ends up being 680. All right, so you notice that when I take n times p hat, I really just end up back with the count that I got from my original problem. Okay, we call this the number of successes. And the number of failures would just be our sample size minus the number of successes. So this 680 is actually the number of failures. So another way to look at these conditions is I can just make sure that the number of successes and the number of failures are both greater than or equal to 10. Okay, and in this case, then they definitely are. So we made sure that successes, failures, they're both greater than or equal to 10, or we could do the multiplication, make sure those numbers are greater than or equal to 10. We're going to do a 95% confidence interval, and we just showed that for a 95% confidence interval, Z star is equal to 1.96. So I'm going to get out my formula. So I have p hat plus and minus Z star times the square root of p hat times 1 minus p hat over n. So remember, my p hat was equal to 0.32. So now I just plug in 0.32 for p hat. I plug in 1.96 for Z star. My n was 1,000. So I can plug all those numbers in here. And then I can work on that calculation. So I'm going to start with the standard error portion. So I'm going to take the 0.32 times 1 minus 0.32 divided by 1,000. Then I take the square root of that number. All right, so this portion right here came from everything under the square root. This is my standard error. Then I'm going to multiply that by 1.96. And then I'm going to be left with 0.32 plus and minus 0.0289. Okay, so this 0.0289, that is the margin of error. And I'm going to add and subtract that from 0.32. So I take 0.32 minus 0.0289, which gives me 0.2911. And then I take 0.32 plus 0.0289, which gives me 0.3489. So this is my confidence interval. And we're going to draw conclusions about this confidence interval, write the conclusion the same way that we did in chapter 3. So we'd say we are 95% confident that the true proportion of all adults who would favor syntaxes is between 0.2911 and 0.3489, or 29.1% and 34.9%. All right, we are out of time, so we won't be able to do our last example there. The other thing that we haven't gotten to in this section yet is figuring out what sample size we need for a desired margin of error. So we're going to hit that first next time, but I just want to warn you of that. If you start on your Wiley Plus homework and it starts asking you for what sample size you need, and you're like, she never talked about that in class. So just hold off on any of those sample size problems from 6.1, and I promise we'll talk about them at the beginning of class next time.